So first of all, let's talk about the point estimate for a population standard deviation, since that's what we're trying to estimate in this section. The sample standard deviation, S, is the best point estimate for the population standard deviation, sigma. The chi-square distribution is what we're going to use when we're estimating a population standard deviation. If a simple random sample of size n is obtained from a normally distributed population with mean mu and standard deviation sigma, then chi squared equals n minus 1 times s squared divided by sigma squared. So in this situation, the chi squared right here is our statistic that comes from our sample. And this has a chi-squared distribution with n minus 1 degrees of freedom. Now the chi-squared distribution looks different than the other distributions we've dealt with. For one thing, it's not symmetric. The normal distribution and the t-distribution both were symmetric on either side of the mean, but the chi-square distribution is not. In fact, it's skewed to the right. Now the shape of the distribution depends on the number of degrees of freedom, just like the t-distribution did. So here are some pictures of different chi-square distributions for different values of n. So the blue one right here is with only 2 degrees of freedom. The red one is with 5 degrees of freedom. The orange one is with 10. The green one is with 15. And the purple one is with 30. So you can see that as the degrees of freedom gets bigger, the chi-square distribution gets closer to being symmetric, and it also sort of moves over to the right. Another thing that's different about this distribution is that the values of chi-squared are non-negative. In other words, this graph starts at 0 and goes to the right. There is nothing on the left side of 0. This is going to make things a little bit different when we try to find critical values from this distribution. Because it's not symmetric, we have to find the two critical values separately. The value of alpha is still divided between the two tails, and we're going to use n minus 1 for our degrees of freedom. So what we'll do is we'll take our alpha, divide it equally between the two tails, so we have alpha over 2 in this tail and alpha over 2 in this tail. So the requirements for doing this are that the sample has to be a simple random sample, and second, the population must have normally distributed values, even if the sample is large. So no matter what the sample size, the original population has to have a normal distribution. Now, to construct this confidence interval, because our distribution isn't symmetric and our critical values are completely different, we just do the two limits separately. We don't actually talk about a margin of error in this case.
Let's go back to this data set, and let's say that we wanted to find confidence intervals to estimate the standard deviations of the waiting times. So instead of estimating the means, we'd be trying to estimate the standard deviations. The thing that makes this a little difficult in StatCrunch is it doesn't have a specific procedure to estimate standard deviations. It has one for variances instead. If you remember, the variance is the square of the standard deviation. So we can use this, we just have to, at the end, we have to take square roots of everything. So if we were going to do this, we would do variance stats, one sample with data. And I'm just going to do this for the overall wait time. I'm not going to group it by the different branches. So notice here it's doing confidence interval for sigma squared, which is the variance. So here's our answer. If you think about what the wait times are, if you look at this and you're thinking standard deviation, these numbers look really big compared to a wait time of 5 or 6 minutes. If the standard deviation was 1.3 minutes, that would be a pretty big standard deviation in comparison. But this isn't the standard deviation, this is actually the variance. So here's why this is a little bit difficult. You have to go in and take the square roots of all these things to get down to the standard deviation. My sample standard deviation would be the square root of this. So my sample standard deviation would be 1.15. And then for my confidence interval, I'd have to take the square root of each one of these two. So the square root of 1.132 would give me 1.06. The square root of 1.549 would give me 1.24. This is my confidence interval for my standard deviation. What this is telling us is that we would be 95% confident that the standard deviation for the waiting times would be between 1.06 minutes and 1.24 minutes.